So this is problem 8.40 or 13A on your homework for assignment 7. And let's see, so we know that roughly 2/3 of all human beings have a dominant right foot or I foot, and we want to know if there's also right side dominance in kissing behavior. So an article reported that in a random sample of 121 kissing couples, both people and 78 of the couples tended to lean more towards the right than to the left. Okay, so for A, if 2/3 of all kissing couples exhibit this right-leaning behavior, that would be a population probability or proportion, since it's for all couples, and we have a sample size of 121. Okay, what is the probability that the number in a sample of 121 who do so differ from the expected value by at least as much as what was actually observed? So, sounds more complicated, but at least it's a set than it is. So first thing we should do is find the actual expected number of couples that will lean to the right. And the expected number, well, anytime you're counting something, it's a pretty safe bet that it's going to be a binomial distribution. You should go through and check, okay, should the couples be independent of each other? Well, they probably should be independent of each other. The probability of them being right-leaning should be 2/3 for each couple. That's the same. Okay, we know in advance we're looking at 121 couples, and each couple can either lean to the right or not. So it is a binomial, and so the expected value for a binomial is n times p, so 2/3 times 121. So 80.666. Okay. So if they all exhibit this behavior, what's the probability that the number in a sample of 121 who do so differs from the expected value by at least as much as what was actually observed? So what happened is in our sample, we had 78 people. Okay. So the difference between the expected value and our observed value is 2.6666. Okay, so for us to get a sample that's at least as far from the expected value as what we saw, is that we need to get x, we need to find the probability that x is less than or equal to 78, because that would be at least what we saw, or worse, further away from the expected value. Or, if we went the other direction, it would be 80.666 plus 2.6666. So we're looking for the probability that x is less than or equal to 78, or x is greater than or equal to 83.333. Now remember, this is a binomial distribution, so we can just find the probability that x is less than or equal to 78 plus the probability that x is greater than or equal to 83.333. And at this point, you need to use a binomial table, calculator, app, Excel, anything that you use to find binomial probabilities. Because you could find them all by hand, but you'd have to find the probability that x goes all the way from 0 to 78 and 83 all the way up to 121, which would take a really long time. So we want to use some kind of calculator. So I just went online and searched for binomial calculator. This is the first one that popped up. Notice as I come through, I need to type in my sample size. So my sample size is 121, and my probability is 0.6666666. Okay. Let's see, so if I want to find the probability that x is less than or equal to 78, then I need the probability that x is, let's see, that would be at most is another way to say that x is less than or equal to 78. So at most 78. Compute. Notice it shades it for me nicely. And our probability is 0.3346. Okay, and then we also needed greater than or equal to 83.33. Now, we're not going to find that exactly in the binomial because it only deals with whole numbers. So if you want to be at least 83.33, that's really the same thing as x is greater than or equal to 84 when you want to deal with only whole numbers. So 84, we want at least, so 84 or above. Compute that, we get 0.2954. So let's go back to our problem. So we were looking for the probability that x was less than or equal to 78, plus the probability that x was greater than or equal to 84, which is 0.3346 plus 0.2954. Which gives me 0.63.